So it's 5/6 of a hertz, and then we're supposed to find length. So then yesterday we found this 2 pi square root of L over G. This equation comes from the fact that omega is the square root of G over L, and then omega is also 2 pi over T. Well, remember, omega is also 2 pi F, right? So if I put these together, we get F is equal to 1 over 2 pi times the square root of G over L. So you can either like take this one and solve it for L, and then remember that T is 1 over F, or you can just take this one, which I think might be in your book, solve this for L, whichever one you want to do. Right, so this is like L is equal to G over the square root of F squared over, just kidding. So F squared like 4 pi squared or something. Move that over, it's F 2 pi F, square both sides, F squared 4 pi squared, and put at the bottom, yeah, so either way, whatever you want to do. If you want to solve this one for L, and get L is equal to G times T squared over 4 pi squared, and then take this frequency, plug it in there, 6/5. You should get the answer. Their answer is 35.7 centimeters, so please double check that. Questions on that?
Up there on the answers, does it say square root of L over R? T equals 2 pi square root of L over R?
L over G.
Okay.
Yeah, sorry, it's a little fuzzy for some reason. It's like there's a PNG captured inside of this PDF or whatever this document is. So, I mean, these are actually Word files. So for some reason, these, you know how like sometimes I can drag those and make them bigger? So they're like PNG files, but when they got transferred to Google Drive, everything looks crappy if you blow it up. Okay, questions on that? We're good? All right. Should I just record each one or just do all of them and then record it at the end? Or like do one giant video of all of them? Giant? Yeah, it makes it easy. All right, so we'll erase that. And then do we 35?
Yeah.
Okay. That's nice and big. All right. So let's see. Somebody tell me what's on 35.
Oh, they give you a graph. And then you're supposed to find, they give 2 graphs in one plot. You're supposed to find the frequency for each graph and the time for something for that.
Okay, so yeah, clearly we're gonna have to look at this instead of graph. Oh yeah, okay. Okay, so 35, the graph looks like 2 graphs up here, 1435. So there's something that looks like sine, and this, or no, sorry, cosine, and something that looks like sine underneath it. Oops. And they give you specifics, and they ask you to find a couple things. A, the frequency of the system. Over B, the period read this a bunch of stuff. Frequency, what's the first time at which the mass has maximum speed while traveling in the upward direction? Alright, so this is y, that's t, of course. Okay, so the frequency of system A, and then if we look at certain points here, we can see that system A goes down like this, up, and it hits can you tell what that is? Is it about every 2?
I think it goes from 1 to 3.
It's like 6 per every 4 units. So it's 1.5 per unit. And then this point right here, that hits on a mark. So that's 9. That right there is 9 seconds. So we know that this is 1.5 waves in 9 seconds. So the frequency is 1.5 waves in 9 seconds. So then I'm going to call it oscillations. So there's your frequency, just by looking at the graph. Just double check to make sure that I heard. 125. Yeah, is that right? Is that right? Maximum speed while traveling in upward direction. They give us a frequency of 0.25. Okay, I'm going to take a picture of this and show us. Let's see if we get it together. I'm sorry? Oh, it's on the day of the final. Okay, so if I look at this graph, what's that? Oh. Yeah. I'm just gonna. Okay, so on here, it seems to me that there's 1, 2, 3, 4 lines for 6, right? 1, 2, 3, 4 lines for 6. So I believe that means one line is 1.5, doesn't it? 3, 4.5, 6. So this should be 7.5, this should be 9, this should be 10.5, and that's 12. So for A, if A goes down here like this, oh, look at that. I did B, okay. Boom. If that's 1, 2, 2.5. Ah, okay. Sorry. So for A should have been the frequency should have been 2.5 oscillations in 9 seconds. It's still not. Isn't that 2.5? 1, 2. Oh yeah, 2.5 would have ended down here, so 2.25. And then 4.5, okay, that does give us 0.25 rates. Okay, let me clear that just so you can see again what I'm talking about. I chose this point. Do you see why I chose that point? Because it crosses exactly at the right, it crosses, it hits right at a number that's marked. And then I just have to remember this is 1, 2, and then that's 0.25. So there's 2.25 oscillations in 9 seconds. Okay, and that does give us our 0.25. Does that make sense? Okay. So with that said, now let's see, what is the frequency of system A? We did that. What is the first time at which the mass has a maximum speed while traveling in the upward direction? Where does it have maximum speed? William, when does it have maximum speed? Okay, think of the rubber band thing. When do I have maximum speed? Yeah, when you get back to the axis, the midpoint, right? So do I choose this one? That's maximum speed, right? Well, what do you think, or Tony?
That's moving downward.
Yeah, that's moving downward, right? So we're going to pick that one right there. So that's at 3 seconds? Everybody go with that? Okay. Then, so let's go ahead. What is the period of system B? So that's fine. System B, we just find 1 right there. So the period is 6 seconds. What is the first time at which the energy is all potential? Okay? How do you know that something is going to be potential energy, Sid?
If it's at the amplitude.
Okay, why?
Because that's when all the energy is potential, because it's at the maximum plus the distance.
Okay, and Erica, how could you witness it visually and say, oh, that's all potential energy? What happens?
Stop.
Yeah, it stops, right? So all the kinetic energy is gone, and so boom, it's all potential energy stored in either gravitational potential or stored in elastic, depending on what we're talking about. Okay, so 2 great answers, thank you. What is the first time at which energy is all potential for B? So we're looking at that point right there, which is at 1.5 seconds. Okay, and then C, if both systems have the same mass, what is the ratio of Ka to Kb of their spring constants? So this is just a little algebra based on everything that we know. There we go. So for this, for part C, basically they're using the period equation, right? Because we can find the period for both, and then we plug it in. Right, so here they have the period of mass A is this, period of mass B is this, and then by doing the ratio of the periods, we can get. Was mass A and mass B equal? Oh, okay. Yeah, that makes life easy. So just a little bit of algebra. Questions on that one? We have a older camera phone, like an old phone with a camera. Maybe not an iPhone or not a. I have a sneaky suspicion that this is an entirely different process than I thought. Look at the tip. See the the hole. It looks like there's a bulb in there. It might be an infrared LED or an infrared sensor. What is that? No. Okay, any questions on this? We're good? We'll move on. All right. Okay. Here. And then 59. Might be a little too big. Okay, so for 59, it says, okay, so how long do the oscillations take at the equator? How long do the oscillations take at the North Pole? I guess I'll just do a big combination of both of these things. Really excited. 3 weeks I'm supposed to get, and I have me. Okay. So, they give us these 2 accelerations, and then they tell us a length of rope or whatever, pendulum. So how long do the oscillations take at the equator? How long do they take at the North Pole? Well, there you go, right? Oops, just kidding. This. T is 2 pi square root of L over G, right? So the North Pole one, you plug in 1G. The equator one, you plug in the other G. 978 and 983. Equator poles. Okay. Yeah, and then you'll get your 2. So the period at the.
Can you record this, please?
It is.
That's one giant video.
Yeah, it's gonna be one giant video. So yeah. That'd be interesting. I wonder if I can. Oh, I'm recording myself recording it. I'm recording myself while recording myself. That way, in case I miss myself, I can go back and listen to myself recording myself. I don't know what that means. Yeah, Inception. Which one's the real one? All right. So anyways, the equator one is just going to be the one, and then the poles will be the other. Because the poles are closer, this is the pole one, and this is the equator one, and you get your 2 different times, or 2 different periods. Then is the difference between your answers to part A and B measurable? What kind of instrument could you use? I imagine it's going to be tiny. So what's the difference? What did you get for the period of the equator? 2 point what? 200.9 seconds. 200.9? Yeah. Okay, 200.9 seconds. I gotta get rid of that random dot. 200.9 seconds. And what was the other one? 200.4 seconds. All right. So is there a difference? Yes. You could use a stopwatch to measure it, but what's the problem in using a stopwatch? Yeah, right. Human reaction time is around 0.2 to 0.25 seconds. So you could almost lose the difference in your human inaccuracy. So if you use a photogate, you know what that is? So a photogate is like you have like a stick with a little infrared sensor. And then you have another stick with an infrared light. Okay, and these 2 sticks, when the light goes into the sensor, red, get it? When the light goes into the sensor, it starts like monitoring. And what you have is you just set up a circuit there with a simple integrated circuit that when something stops the light beam, then that triggers a time circuit to begin counting. And then when it triggers again, that tells the time circuit to stop counting. So then you could hold your pendulum up here, swing it, and it'll go through at the bottom, go up, and come back down through. Now, if these are our periods, how long, what time is that going to give me? What's it going to say on my readout? Is it going to say 200? 200 point something? Ah, nice. You see that? It should say 100 because it's only half, right? It started at the bottom, went up, and stopped when it came back down. But that's an example of what you could use to measure that. And then suppose you take your gravimeter. At the top of the highest mountain peak, there you find 100 oscillations. Okay, so if you take it to the top of the mountain and 100 oscillations takes that much time, then you can just set that equal to the equation, right, and solve for G. Okay, so that's there. That's funny. Okay, so I don't think I need to do that. That's pretty slow. Okay, and that's hopefully what they've showed us here. If we take a look, yeah, we did this, and look, we're right like 200 second. Did you say 2.09 or did you say 200.9?
Because it's for 100.
It's you find teams only for one oscillation, so we have to multiply everything.
Oh, okay, cool. All right, so that's fine. The difference, okay, quite measurable, hand operated, yeah, sure. But I mean, yeah, it's measurable with a stopwatch, but you're going to have humongous error. So I don't know. I wouldn't choose. I would choose some sort of electronic timing system, but whatever. D, and then here they're saying the period is this. They got that by taking the oscillations divided by the time, and then just plug it into your equation. Right. It's just the T is 2 pi. Square root of L G. So once again, G is equal to T squared over 4 pi squared minus 1 times L. Yeah, sorry, that's pretty lame way to write that. You write that and be less confusing. Okay, so I guess the easiest way to write that is L times 4 pi squared. Over G squared. Just plug everything in and get checks. Questions? All right, on a side note, Pavin came in and asked some questions this morning. He asked one question, and let's see how if this works out for everybody. Remember this question? Yeah. Okay, so here, and of course, Pavin immediately, I was like, oh, just use the law of cosines, right? And then I wrote out this. And then for theta, use 106. Yeah, see, that was my mistake. That's why it came out to be the wrong answer this morning. Because when you add vectors, remember, it's got to go head to tail, head to tail. So you'd have to take this one, put it here, or you could use quadrilateral. Yeah, you can use a quadrilateral method where you just draw the quadrilateral, the parallels of these. This is parallel to this, and this is parallel to that. And then, of course, this angle is 106. So this angle has to be 74, right? because same side angles have to add up to 180. So that angle right there should be 74. And if I do 74, that would have given us the right answer.
Wait, R is that there?
Yeah, R is this right here. Well, okay. Technically, we say so it's like when I add those two, I get this, and then R is the negative of that. So if you crack these, see that was the interesting thing that we ran into, right? Because how do you crack them if you know the angle between them is 106, but you don't know the angle of each? You know what I mean? Because if you make this theta, then this is 106 minus theta, right? Because like it comes out to be something like 20 sine theta is going to be equal to 50 sine 106 minus theta. How do you solve that for theta? Can any of you in here solve that for theta? Yeah, I'll be honest, I couldn't figure out what to do. I couldn't see what to do. Okay, that's fine. I feel better. Yeah, so just use well cosines. Yeah. Yeah, you just have to like.
It's not on the other sheet.
You have to use the good old system that I used when I was your age. Interpolation. Because they give you some things, right? Like they give you 45, they give you 60, they give you 57, they give you 33. So then you have to know like, okay, cosine of 74, cosine goes like this, right? And this is 180, that's 360, right? This is 90, and so you're just guessing. You know like 45 right there is 0.7071, right? And so then from that, you go, okay, it's going to be around in here. So I would guess like, I don't know, 0.4 or something, or 3. And then if you multiply that by that and do all that stuff, then you're going to answer close to 50. And that's, because remember our answer was close to 60, even though we did, you know, our head. Yeah, that's fine. That was admittedly a hard problem. Like, there are problems, and you'll discover this when you go to college next year or 2 years. Like, most professors that you'll cover, they'll put like a problem that everybody's supposed to get. And then they'll put a problem that's supposed to be like, you know, if you're paying attention, you should be able to get it. And then they'll put a problem that's just mind-numbingly difficult. Or we get the guys who do every problem is built like that. The first part is easy, second or third part is like middle, and then the final part is like insanely impossible. Like it's to separate the adults from the children. I guess. I didn't want to say men and boys because that's. Okay.